Let us now discuss a linear power supply, this circuit. We have discussed the theoretical aspects of this circuit earlier. It will be interesting to simulate this. As you see here, there are two new components, NPN transistor, BJT, and an op-amp. We saw recently how to incorporate a sub-circuit model for an op-amp and link it with a symbol. So this we developed, and then we have incorporated them in our custom library. Let us use the op-amp that we developed and use it for simulation. So here I will have just a input AC source, the diodes, the capacitor, BJT, and all this part of the circuit. Recall this or refer to your old circuit. Let us begin. So I will close this and keep the KiCad open, the KiCad dialog box. Let us create a new project. I will create a new project and I will call that one as linear power supply. So linear power supply. It should also show up here as linear power supply in our folder. So let me take the schematic, double click on the schematic. And you have this schematic appearing here. Let me first give a title. Also linear power supply using op-amp. So this is the title for this sheet. I'll place it here. And next I need to load up the components. From this icon, I will use this icon, add symbol, and bring the components, load up the components. So let me click on that. So if you see here, all the components that are here, you don't see my components library that we have created. That is because we created a new project library. There is no way that the project is able to link to the model and the symbol that we created. So we have to bring that into this project. How do we do that? So let me come out of this. Let me keep this here. Okay, or let me close this, save. Okay. So I will go into the folder mode. We had kept the model and the symbol in this full wave rectifier project. So I will copy them. Copy and place them in the linear power supply project folder. So now that they are in the folder, let us give the path in the, I'll go into the symbol editor or even the schematic editor. Let me go into the schematic editor. Go into preference, manage symbol libraries. So you have the global libraries which are available for you to use. I want to go to project specific libraries and I will browse, and in the particular project that we just created, we copied the symbols, go in, and we have created this previously, and let us open that. So now that is included in the project specific libraries. Click OK. and it should now reflect when I click on components. Let me add symbol, and let me see here. So now you see that it reflects here in as one of the library components, my components. This is the library that we had custom created. There are two components, diode, power diode, and the op amp. So we will use the op amp. We will use the op amp. I will bring that in. We need to take in the default diodes also. So I will pick up the diode. We need 4 diodes. And we need a source. I will pick up the source. Then we need a transistor. I will use TIP41. You can look at the data sheet of the TIP41. It's a 6 amp device. I will place that there. I need a capacitance. I need resistances. So I will pick one resistor and place it, and then I can copy duplicate that. So what I will do is that I will change the cursor. I will make some space here, and I will make duplicates. Instead of this diode, let me pick the diode that we made, that we created. So let me pick this, and let us use that. I will remove this diode. Yeah. Okay, we duplicate 4 of these. I'll control copy that and then paste 1. And 1 more here. So you now have 4 diodes. I have a capacitance. Let me position it in this fashion. Let me flip the op amp in this fashion so that it will come in something like, let me position it properly, like how we have it while discussing the theoretical part. Now let me copy the resistors. I will need a resistance division here like this, and a load resistor. This will be the load resistor. And then I will need the ground. Let me go to the add symbols. Let me say 0. So I need the power ground. Reference pin. This is the reference pin. So let me paste that here. And now we are almost ready to do the wiring. Before that, let me copy. I will copy the power supply, place it here. I want to have a 0 power supply for measuring the currents here, and then one here. Yes, let us place that. I will clear up the clutter. So what I will do is this. So this is going to be a 0 power supply, 0 amplitude, 0 frequency. Okay. Same for this, because this is also a current measurement. So these power supplies are supposed to be current measurement supplies, which are 0 amplitude and 0 frequency. Now let me make everything invisible except the reference, right? So this alone will show up. Same way for this also. I will adjust this position. Let me hide all these things so that there is no clutter, and I will position it like this. I would like to have one more resistance here to limit the current into the base, or to limit the current source from the op amp. Okay, so more or less we have all the components here. So let me now make the circuit wiring diagram. So wiring diagram will be quick. Then from here to here, these two also I can connect. I'll connect this to this and this here, make the connections in this fashion. You almost have the circuit through. So the wire cursor has snap-on facility. So this will actually ease your circuit wiring efforts. Let me position the capacitor a bit to this side so that we can have a much easier wiring connection, like that. Then you wire up the input sine wave. So we are almost through, and the load like this. So now here there are a few things which we need. You need power supplies for the op amp. You also need some reference, which I can give as a DC source for now. So let me go back again to the add symbol, and I am going to ask for VD. So let me choose this. This is just a simulation reference. So I will place one here, and I will need two more. I'll explain why I need two more. Two more I need for generating the power supply. So let's say that I have set it up like this. So now let me wire it up. This and this I'm going to connect. I'm going to connect this with this, and I'm going to connect this to the reference ground. The reference ground is going to be like this. So I have connected the reference ground. You have a 0 node. I will also copy this 0 node and paste it here, and let us connect it here. Then I will need two labels. One will be VCC, call that VCC, which I would like to connect here, and one more VEE as a negative power supply part, and again back to wires and make the connections. So now you have in this sheet VCC, which is plus 15 and minus 15, if I give the values in this fashion. So I will say this is 15 volts, I will say this is another 15 volts. So 15 volts with this as plus means this is minus. So VE would be minus 15 with respect to ground. VCC will be plus 15 with respect to ground. Now I will copy this, paste, and copy this and paste it here. So let me now do the wiring so that this is connected here and this is connected here. That is fine. Now we have almost everything in place. We need to assign the values. So first this, let me do 20 volt amplitude sine wave, because after it is stepped down the transformer, it is a reduction in voltage from the 230 volts mains. So I am going to step it down like this, and this is 0, this is a current sense capacitance. Let me have 1000 microfarads capacitance. Tip 41, I will come back to it. Let me have 100 ohms here. Let me have here another 100 ohms at the load, and this is a step down. So you see that I am having 20 volts coming here approximately. Let us say that we design for an output of, so let us say that this is 2 volts reference, and if I say that this is 10K and this is 30K, so whatever V0 into 10K divided by 40K will be 2 volts. So, or if I am setting this at 2 volts virtual ground, this will be 2 volts into 4 times, which will be around 8 volts. Okay, so that's what you can expect. So that's why I am setting this 30K, not just 30 ohms, it's 30K. Okay. So everything is set except TIP 41 model. See, in the case of the diode, if I double click, you will see that it will refer to this folder and take the model from there. Likewise, op-amp is also sub-circuit. It will take from this ludevices.lib, which we have already created. Tip 41 alone, I have not created a model. What I can do is, just like we did and one of the earlier simulations, I will take the model from the internet and then copy it and paste it. So let me open this. So let me open a notepad file. So in the linear power supply project folder, I have placed an empty notepad file. It's a text file with extension .lib, and I called it bjtmodels.lib. So it is empty. So if I click on that, this is what it is. I will say the spice model of BJTs. Okay. So now I'm going to copy the spice model. So if you go and search on the net, you will find spice model of BJT with this TIP tip 41. So let me copy that and paste it here. So this is the spice model of tip 41. It's an NPN transistor with these kind of parameters. Save that. I'll save that and I will close this. Now here, let me go double click. So here I can go into the simulation model. Go into the simulation model. Let me pick that file, BJT models. I have BJT models. This is what I created just now. Open that. So here tip 41 is there. Click on that. Then look at the pin assignment. They should, if they are not matching, you have to see that it is addressed. See that in the symbol, 1 is representing base, 2 is representing collector, 3 is representing emitter. But in the model, it is collector and base are interchanged. So you will have to take care of that. So what you have to do, let me go back here, go to edit symbol, click on that. So the symbol page comes. I need to interchange collector and base. So let me expand that. So let's say this is the collector. So the collector has to become pin number 1 because that is referenced 1. I'm going to interchange that. And the base, and the base becomes 2. Save that. And now again you can see, going to the simulation model, let us load bjtmodels.lib, choose tip 41, pin assignment. Now it is alright, C to C, B to B, E to E. Now things will work. Right? So if you patiently take care of all these things, you will generally not go wrong and simulation will normally work for short. So let me click OK. So we have everything in place. I will save this. And now you can give the control statements. So let me make some space here. And click in the text box .control. As we did earlier, I will also put the option statement, relative tolerance 0.01, absolute tolerance equals 0.01, V and tol equals 0.01. So I will have the option statement also. Then the transient analysis statement, Transition analysis with a maximum step time of 1 microsecond up to 100 milliseconds. Use initial initial conditions, and then I will give run. Then don't forget to set color of the background equal to white. Of course, this is optional, but I prefer it this way. Background color to white. Set color of the foreground to black. Set foreground color to black. Then plot .nc. So I will leave that plot here. I'll come back again. Let me left justify and place this here. Now let us put in some labels. I'll pick this add label. So A, this is going to be my A. This is going to be my B. Then this is going to be my C. Then this is going to be the output, O. Then let me give the midpoint here. I will give some X, right? And I can give another value here, Y. Let me place them here and connect them. All these labels, let me connect to these respective nodes, and then you are ready to generate the netlist. So let us now generate the netlist. I will save, export netlist, spice netlist, export netlist into linear power supply.cir. So you save it into that. So the netlist has been generated. We have forgotten to give the plot variables. Let me double click and give the plot variables. V A comma B for the input, VC for the capacitor output, capacitor voltage, and V naught for the output voltage. So so you see that it is created here. Again, let us save, export netlist, and that is saved as .cir file. So when I open the netlist, the linear power supply.cir, so you see that it has created a reference for the BJT models.lib, where it will go and look into that file, and it will also look into LU devices.lib. This is the custom library that we created, library of models for both the power diodes and the op-amp. So note that the diode being referred to the power diode that we created and the op-amp subcircuit that we created. Now these two libraries are defined in LU devices. For example, if I go in there, in the models, in LU device, if I double click, you will see the power diode subcircuit is here, the op-amp subcircuit, whatever we have created, right? So let me now execute this .car file in the ngSpice environment and see that behaves as linear power supply. So let me bring in a command window. So in the command window, let us say ngspice linear power supply.cir. So these are the waveforms that we had requested ngspice to plot. VAB, this is the input voltage, the red signal. The blue signal VC is the voltage at the capacitor, rectified, full wave rectified output of the capacitor, slightly lower than the input because the diodes that we have used are not the default or the ideal diodes, they are the non-ideal diodes. And the orange waveform is the output waveform, and you see that it is at around 8 volts. You can zoom into this point and then see that it's around 8 volts. So you can do a loading and see what happens. So now let's say that I will alter R1, which is the load. Observe the load there, R1 to 500, and then run the tran 1 microsecond and 200 milliseconds UIC. And now again I will plot VA comma B. I will also plot the C and V naught. So you see that I have loaded less because I have made it 500. I made R1 as 500 ohms, and because of that you see that the ripple is lesser because the load on the capacitor is less, and this is regulated to the same voltage. Let me also load it more. I will now alter R1, this one the load, R1 which is the load, to let's say 50 ohms. I'm drawing more current and tran for 1 microsecond, 100 milliseconds UIC. And now again I will plot V A comma B, VC and V naught. So you see that the ripple is now higher because of more load, but still the output is regulated to 8 volts. If you want to look at, you can see that if I want to look at this voltage, I have not joined this. Okay, if I want to look at this voltage, let me join this quickly. I will save and then export the netlist there. So let me go to the command window and run that simulation. Let me plot Vx, this one. So it should be same as this, around 2 volts. So the moment you have 2 into 10 divided by 40, 2 into 40 divided by 10 will be the V naught, or V naught into 10 divided by 40 will be 2. Okay, so if I plot Vx, it will be around 2 volts. So which means that if this is 2 volts, then I know that the op amp is working and then it is operating in closed loop. So this part is operating in closed loop. So hence you can verify the working of a linear power supply. Of course, you can vary several of the resistors and get a feel for it. You can change the ratios. And then see that the output voltage will conform to that new ratio. For example, if I had a different ratio, so let us say if this is 40, 40K. So now V0 into 10 divided by 50. So V0 by 10 will be 2 volts, or V0 into 10 by 50, which is V0 by 5, which will be 2 volts. So therefore 2 into 5 will be 10 for output. So I should get 10 instead of 8. You could probably run this. Let me save that, export the netlist, and quickly generate the CIR file, and you will see the CIR file. Here we changed the value of the resistance. So one is 10K, the other one is 40K. So this is the latest updated CIR file. Let me go here to the exit and let me run the CIR file again, and I'm interested in seeing plot V of X. This is the attenuator midpoint. So now this is 2, and what is the output? Output is 10 volts because we changed the ratio of this so that you can kind of set what output voltage you need or you want. Okay. So this way I will leave it to you to kind of tweak the various parameters and learn about this circuit and also learn about the simulation. And the key takeaway here is we have used components which we have custom built. We have the custom built model of the diode, we took the custom built model of the op amp, and also we put an external model for the transistor here.